For those of you that aren't familiar with Vladimir Sedivy, he's president of Salt Partners, based in Switzerland. He received his MSc degree in chemical engineering at the Institute of Chemical Technology in Prague and a PhD diploma at the Institute of Management Development in Lausanne. He invented the hydrocell salt purification process with hydro extraction of impurities in 1978. So please welcome Vladimir Sedivy, solar salt for the chlor-alkali market. Thank you.
Well, thank you very much for this nice introduction. More than half of all the salt that is produced in the world goes into production of caustic and chlorine, and also soda ash. For that reason, I think that it is important to realize what the importance of impurities in the salt is, the non-salt component of every salt. And therefore, I would like to skip these introductory remarks about the quantity of the salt and the use of the salt, because that was better and in more detail introduced by the previous speakers. So, when salt for chlor-alkali production, particularly of caustic and chlorine production, more than soda ash, and I will explain later on why. When salt for this caustic chlorine use is being produced, then it's a question of purity and composition of that salt, whether the salt is suitable or whether it is not suitable. If it is suitable, then it fetches good prices. If not, it is sold at a discount. The salt prices depend on salt purity, and with the solar salt use and with the question of the prices, we are working somewhere here, somewhere in that curve, getting towards $20 and more per ton and approaching the 100% purity. Now, because it is a curve like that, and the curve is quite steep in that region, it depends on, or it's the interest, and whether it is good or not is then a question of just of a small fraction of a percent. Impurities in salt, the main one is calcium sulfate. It is present in rock salt, sea salt, lake salts, in brines. Magnesium salts are mainly originating from the seawater and are therefore present in the sea salt. Calcium chloride and sodium sulfate are not present in seawater, and therefore they are also not present in solid salt. But potassium chloride and sodium bromide are the main trace elements in salts, in all salts, and they play a certain important role in certain applications of the salt and of the chlorine production, particularly in organic synthesis, where bromine is a problem. Potassium is normally not a problem, simply because potassium is producing also hydroxide in the electrolytical cell, and actually is heavier than sodium, and therefore with the same amount of electricity you produce more caustic. So therefore the potassium is normally not a problem. The title here, that the impurities in salt in 1996, means that these are the impurities we were analyzing in salt in that year. And 30 years later, we are analyzing salt for caustic chlorine production for all these trace elements, main elements and trace elements. Simply because it was found that several of these trace elements have a negative influence on the electrolytical membrane, that it can damage the membrane, and therefore it is not desirable to have it in the salt for caustic chlorine production. Some of these impurities are less important, such as heavy metals and iron and so on. They are polyvalent, they form polyvalent cations, and therefore they are removed in the ion exchange unit. But soluble silicium, for example, and bromine and iodine are not removable in the normal brine purification process, and they can damage membranes. If there is a lot of bromine in the salt, then some special bromine removal technology has to be employed. These are the specifications by two membrane licensors. You can see that the level of impurities is extremely low that they are requiring. Iodine less than 0.1 ppm, silicium less than 5 ppm, and so on. So the requirements are very similar, and they are very, very strict. The basic chlor-alkali equation is very simple. It's sodium chloride and water plus electrical energy is producing sodium hydroxide and chlorine and hydrogen. Now, at this stage, I would like to ask you whether you know what sodium is. Who knows how sodium looks like when you have it in the laboratory? Who knows that? One? Nobody knows. Well, two. Sodium is a metal, very soft metal. You can cut it with a knife. And it's in a state of very high energy content. At the university, we have taken a piece of sodium metal. Normally, you have to keep it under petroleum because it's very energetic and it oxidizes very quickly, it can burn and so on. So we put it quickly in a piece of paper and went to the toilet and threw it in the water closet and let it flow down. And within about 1 minute at the latest, there was an explosion in the piping, because the sodium reacts with water, produces sodium hydroxide and hydrogen, and the hydrogen mixes with the air and explodes. So this is this one that explodes. This is just to explain why so much electrical energy is required to produce from sodium chloride, which is a very low energetical component, to produce these two highly energetically loaded components such as hydroxide and chlorine and hydrogen. The basic chlor-alkali equation for soda is sodium chloride plus calcium carbonate, which is limestone, something that is of very, very low value, to produce soda ash that we need to produce glass mainly, and several other things, plus calcium chloride. Why do we need pure brine for chlor-alkali manufacture? Because there would be damage to the membrane cells, because there would be hydrogen evolution in the mercury cells, incrustations in soda ash production, particularly with calcium sulfate, contaminated effluents, bromine and chlorine for organic synthesis, and so on. The brine purification systems For the calcium precipitation, we have calcium and carbonate producing calcium carbonate. Calcium carbonate is what the soda ash has been produced from, and in the brine purification it is again recreated. The magnesium precipitation for that in the caustic chlorine industry, mainly sodium hydroxide, is being used. The brine purification requires overdosage of reagents. It is about 0.4 kilo per cubic meter of brine of soda and 0.15 of sodium hydroxide. This must be so because otherwise the solubility of these insoluble components, the calcium carbonate and the sodium hydroxide, is too high. So overdosage has to reduce it. Now this is important to know, because if the salt quality is insufficient and variable, then this overdosage has to be done always to cover all the peaks, because you cannot sort of follow hour by hour what you are putting into the saturators. You just have to have a safety margin. So if you are using a very good salt, you are still overdosing and you are spending money on that unnecessarily, and you are then feeding the cells with too much sodium carbonate, which then is decomposed in the cell, and carbon dioxide is being produced together with the chlorine. Sulfate removal, the classical methods are with barium. Barium carbonate is fine. Barium chloride is poisonous, so it is not preferred, and calcium chloride requires large volumes and long residence times, and is a bit difficult process. Now, for the nanofiltration, this oval, the blue oval, that one over there, that is the concentration of sodium sulfate in the electrolytical brine, and to get it out in a nanomembrane, the brine needs to be cooled, and then it can reach this nanofiltration operating point, this one, at which then the solubility of sodium sulfate is very high, so that it can be removed. Regarding the cost of brine purification, we have done a survey with these companies who very kindly gave us the information how much they have to pay for brine purification chemicals, and some of them have given us an insight into several other costs that are incurred if the salt quality is not sufficiently good. So the brine treatment, cost of the brine treatment and the cost of the salt vary greatly in the input into the caustic chlorine plants. They can be as low as $1.50 per ton of salt and as much as $30 per ton of salt. And if we take also the cost of brine treatment and disposal of these impurities, and they have to be disposed of as chemical impurities, although they are just a limestone, really. So the cost of that disposal can be significant, between $10 and $60 per ton of salt. So you can imagine that if the salt is not well purified and not sufficiently good, then the incurred costs can be very high. This is the relative brine treatment cost as a percentage of the salt cost. So minimum 100%, but the impure salt can cause costs that are 3 times higher. And as a percentage of chlor-alkali production, 3% is, well, very little. But if it is 4%, then it is very significant. The rest of the cost is mainly electricity. So, how did we develop the process, and how did we went about improving the caustic chlorine production from the point of view of salt? Well, back in 1979, we have built a caustic chlorine plant in Egypt, and for that we have bought a salt washing plant from a famous French solar salt producing company. This one here is the washing plant. I was given the job to develop some, well, to start it up and to develop some knowledge about this. And when we started getting data, this was the line. We thought, well, this is fantastic. This is a beautiful correlation. We make this line, we make this correlation. If the raw salt has so and so much impurities, then the purified salt will be like this and this. However, the next day or the next few weeks it looked like that, and after a couple of months it looked like that. So we have learned that there is no simple correlation between impurities in raw salt and in purified salt, and that we have to do something quite different. So we had to study the nature of impurities, the phase equilibria of brine components, structure of salts, crystals, salt and brine contact time, and the unit operations. So we have taken a look at the salt, how it looks like. On the left-hand side it looks beautiful, on the right-hand side we see that it is not homogeneous, that the solar salt has a lot of cavities and crevices, and these of course are full of impurities. We have borrowed a mineralogical microscope from the University of Zurich and have made some photographs here. On the left-hand side, the normal light, in the middle polarized light, and on the right-hand side, the partially polarized light, which then shows both the sodium chloride and the impurities. We have then identified these impurities. We have, of course, first we had to identify them. We have created them. We have synthesized the impurities as astracanate, as bitter salt, and as calcium sulfate. We have then found out that the calcium sulfate particularly can be removed from the salt by crushing, that it actually falls out from crushed salt crystal. We have found out how to elutriate these calcium sulfate crystals on the left-hand side. And we have also found out that if we are just trying to wash the salt, then we are washing, dissolving, and at the end we just have only impurities and no salt left. This shows that even after a very thorough purification with saturated brine, which does not dissolve the salt, we still have some impurities left. The left impurities, these that are not removable, we call them aggregability of the salt. We had to establish the phase equilibria of the system: sodium, magnesium, chloride, sulfate, and water. And these are this is the phase diagram that shows saturated solutions, saturated magnesium chloride, saturated sodium, sulfate, saturated magnesium, sulfate, and saturated sodium chloride. The diagram, every producer of solar salt knows or should know, because in the crystallizers, the crystallization of sodium chloride occurs according to this phase equilibria. And in the hydrosol process, we have reversed this process, and we then actually crystallize the sodium chloride out of the purification solution. We are not washing the salt, we are actually crystallizing the salt from the washing brine back on the salt crystals. The principles of the process: we have a centrifuge and we have filtrate from the centrifuge. The filtrate always contains some fine salt. We are taking this fine salt, adding a little water, dissolving, and creating pure saturated brine. We are returning the pure saturated brine into the hydroextractor, where the brine flows against the salt crystals and is picking up the impurities from the salt. We are transporting the raw salt by hydraulic slurry pumping from a luterator into the hydroextractor, and we are circulating brine through a settling pond for adjustment of the velocities, of the rising velocities in these vessels, in the various zones of the vessels, to provide the purification unit operations. The unit operations are elutriation. When we have large salt crystal in a brine, it falls fast, according to the Stokes law. The small particles of salt and gypsum fall slowly. So if we reverse the flow of the brine upwards, then we are still receiving the large salt crystals by settling, but the gypsum crystals and the fine salt dust gets lifted into the overflow of the elutrator, and thus we are purifying the salt of the insoluble calcium sulfate and insoluble contents. The hydro classification is a bed of salt crystals that is slightly fluidized, and then we can also remove any remaining impurities or fine particles, calcium sulfate, by fluidization with upwards flowing brine. The hydroextraction is taking place according to the phase diagram that I showed you before, and the pure sodium chloride brine, this is this 25% here at the bottom, is then passed through the bed of the salt crystals in upwards flow, is picking up the magnesium chloride, magnesium sulfate, and these are displacing the sodium chloride from the solution, which then crystallizes on the salt crystal surface. So we are dissolving the salt, but we are also recovering the salt, and therefore the final losses in the process are very low, in the order of magnitude of 3%. The hydroextraction does not work always very well if the shape of the hydroextractor is not correct. Then so-called rat holes are being formed, and they are, of course, pulling the impure brine into the pure brine. Everything is mixing up, and it does not work. That it works, for the verification that it works and how it works, we have built a pilot plant at the University of Erlangen near Nuremberg, and this was the result. We had these salt particles flowing down and the brine flowing up, and injecting black brine into the white brine. And we have seen that what is black here only moves upwards, and there is nothing going downwards, that after some sufficient layer of the salt crystals, the black brine is distributed towards every crystal, so that the purification takes place across the whole cross-sectional area of the hydroextractor. Solar salt from poorly managed salt works is not homogeneous. It forms agglomerates. These agglomerates are soft. You can break them up by just between the fingers. And of course, you can imagine that if you have an agglomerate of small crystals, that the space between them is full of impurities, and that it is quite difficult to get these impurities out. So this type of salt can be purified only with crushing. Biologically managed solar salt works are also producing very good quality of solar salt, hard and homogeneous monocrystals that don't contain impurities inside. And these can then be purified very well in the purification plant. Biosalt process results. We had this salt to start with. This one is here on the left-hand side. This is the so-called 96 harvest. And in 2006, after the application of the biological management techniques in that salt works, the improvement was on calcium by 96% and sulfate 46%. And the upgradability of the salt has improved very significantly from 0.07 to 0.03, magnesium from 0.02 to 0.0008, which then gives an excellent calcium-magnesium ratio of 4:1, and the calcium-magnesium ratio is extremely important for brine purification because it facilitates good precipitation of calcium together with magnesium hydroxide, and it improves its settling properties and its filterability. Here is the difference between the 1996 salt and the 2006 salt, again shown in graphical form. We are building these salt purification plants. One of the first one was built in 1980. 15 tons per hour salt export plant, still operating, still running from Monday to Saturday every day, except for Ferragosto, 2 weeks, but only for the workers, not for the maintenance people. Here is a plant that we built in Portugal, and this is the hydrosol purification plant with excellent quality. We claim, and we can prove it, that this is the purest industrial salt for caustic chlorine production in existence. It has slightly over 50 ppm of insolubles, which compares favorably even with any vacuum salt. We have experience with rock salt upgrading for caustic chlorine production, and we have carried out some detailed differential cost in a membrane cell plant for 300,000 tons of chlorine per annum. These are the elements that we were looking at. You can see that this is not just the purification of the brine, but there are several other elements that are relevant to cost of brine purification in caustic chlorine plant. These are the elements of the cost. There is the salt storage and handling, which with pure salt is much easier than with impure salt. Salt dissolution, brine purification, contaminated sludge handling and disposal in Europe. The disposal of these chemical components from the brine purification plant cost about $1,000. So per ton. So it is very expensive. Then the use of ferrocyanide, silica, bromine, iodine, power consumption, hydrochloric acid consumption in the cell and membrane life are the elements of cost in caustic chlorine, and they are all related to the quality of salt. We also looked at some commercially available vacuum salts, and we have seen that these are not necessarily very good. That, for example, one which is very good actually. I mean, on the market it's considered to be a very pure salt, but it has 108, or what we analyzed was 118 ppm of sulfate, but then we found out that actually 70% of that or more is still removable. It's on the surface of the crystals and could be further improved. This is another example, very similar, around 200 ppm of sulfate, and this is a third product which is rather impure with 820 ppm of sulfate. This would be not really very good even for solid salt. The operation of the membrane plant with the salt A, B, and C is shown here. We have washed soda salt with 98.9% purity as an example. We have a good quality of soda salt, hydrosol, salt P. We can reach 99.95%. And an ultra-pure salt, which would then be 99.99, that's the one that we have been producing in that plant I was showing you before, the hydrosol plant in Europe. The operation of these plants with the salt A and C was calculated here in great detail. It was the 300,000 tons per hour chlorine plant, where we have done a detailed technical audit and received all the data. And these were the elements that we were looking at. And the result is that if the salt, washed salt 8 delivered to the plant costs €27 euro a ton, then a very pure salt could be sold or supplied for $46. So it is about 75% higher price. It's the equivalent of that, okay? And this shows what is the importance of the salt quality for the caustic chlorine production. So, how to turn salt into gold? Very simple. You produce it at this cost and you sell it at that price. So, why don't you turn your salt into gold? Thank you.